Hello, and welcome to Chapter 8.4, our final section of the class. So in Chapter 8.3, which we skipped, the topic of 8.3 is just on solving non-homogeneous systems of linear differential equations. So in other words, where the f is not zero. And the same superposition principle applies from Chapter 4.4 due to linearity. The general solution will be xh plus xp. And we would do this by first solving the homogeneous system to find xh, and then using method of undetermined coefficients, or similar, to find a particular solution, and then the general solution is xh plus xp. So, for example, if we were solving this non-homogeneous system of linear differential equations, the first thing that we would do is look at the homogeneous complement. The homogeneous complement is obtained by just deleting the non-homogeneous component. And we get that x sub h, the solution to the homogeneous complement, is, we solved this problem in the Chapter 8.2 lecture. We got that by finding the eigenvalues and eigenvectors of this matrix. And then once we have xh, then we need to find what is x sub p. And we would guess that x sub p is an arbitrary linear combination of the derivatives of the components here. So the derivative of e to the 2t is 2e to the 2t, basically the same thing. And derivative of sine is cosine, derivative of cosine is negative sine, and it loops back around. And likewise for the second entry with other unknown coefficients. And then we would plug that in and solve for k1, k2 out to k6. And we would get our xp. And then x, the general solution to the original equation, is xh plus xp, just as in Chapter 4.4. And that's the method. So as you can see, plugging this in to this equation, we'll have a system of 6 equations and 6 unknowns. We'll equate 3 coefficients in the first row, 3 coefficients in the second row, and have a total of 6 equations, and we can solve those 6 unknowns. And it's very tedious, but it's not difficult in theory. It's like 4.4. But because of that combination of tediousness and that we can do it, it's just a system of 6 equations and 6 unknowns, and then it's xh plus xp. That's why we're skipping it. So we know how to solve homogeneous systems of differential equations if they have distinct eigenvalues. And given a good amount of algebra to solve for unknown coefficients, we could definitely solve non-homogeneous systems as well. But what about when an n by n matrix does not have n distinct real eigenvalues? Then what do we do? So for example, consider this matrix equation. Let's see what happens if we try to find the general solution through finding the eigenvalues and eigenvectors of this matrix. Okay, so what are the eigenvalues? That is where the determinant of a minus lambda I equals 0. So that is finding where is the determinant of this matrix equal to 0. And the determinant of a 2 by 2 is AD minus BC. That's our AD minus BC. And we get that lambda equals 1 is the only eigenvalue. So this is a system of 2 differential equations with only 1 eigenvalue. And if we find the eigenvector for this, then we would get that we're solving for where a minus lambda I v is 0. So what numbers can we put here and sprinkle down so that we get 0? Well, this column here is zeros, so we can put anything there at all. And no matter what that is, in order for this to sum to 0, we need to put a 0 there. So the only eigenvector is any multiple of 1, 0. And then the solution, well, we know that it would be c1 k1 e to the lambda 1t plus c2 k2 e to the lambda 2t. So here that's c1 1 0 e to the 1 times t plus what else? So the point is that this matrix has only 1 eigenvalue, and that 1 eigenvalue has a 1-dimensional eigenspace. So we are missing what the other solution is. We can't get it via the eigenvalue-eigenvector method. So this must have a two-dimensional solution set, since it was a system of two differential equations, but we have only one eigenvalue. So we need to do something else to get what that other solution is. So if this is the case, where when you're solving these, you wind up with fewer eigenvalues than there are equations, then what you'll typically need to do is what the topic of this section is. And before we get to that method, we need to introduce matrix powers. So where A is a square matrix, a matrix power A to the k is defined in the obvious way. A to the k means A multiplied by itself k times. So for example, where A is 1, 2, 3, 4, find A cubed. So first, we would find A squared. A squared means A times A. So we multiply this matrix by itself. And we get 7, 10, 15, 22. That came from, remember, taking this first matrix and we multiply it by 1, 3, the first column. Multiplying it by 1, 3 gets 7, 15. Multiplying that matrix by 2, 4 gets 10, 22. And review the Chapter 8 preliminary lecture for how to do matrix products if you want a review of that. And to find A cubed, so first we multiplied A by itself once, and then A cubed, that is A squared times another A. We just found what A squared is. So we take that matrix and multiply it by A. And that is 37, 54, 81, 118. So repeated matrix multiplication. And also definition. We'll sometimes need to take a matrix to the power of 0. And any number to the power of 0 is 1. Any matrix to the power of 0 is the identity matrix, because it needs to be the multiplicative identity. And here's the big idea. So to solve a differential equation x prime equals ax, where we might have typically written this as like just y prime is 2y, what's the solution there? It's c times e to the 2x. The derivative of ce to the 2x is 2 times ce to the 2x. So we're talking here about a simple, at this point, single differential equation. We can recognize that because the derivative of e to the at is a e to the at, then therefore e to the at is a solution. So to solve a differential system, capital X prime equals ax, where now that's a matrix and x is a unknown column vector, if we can come up with some definition of matrix exponentiation such that this same thing applies, the derivative of e to the at is the matrix A times the matrix e to the at, then in the same way, e to the at would solve the system. And to find such a definition of matrix exponentiation, what we can do is look at what is the definition of e to the at in the first place. Well, e to the at is defined by its Taylor series. You take the exponent and plug it into sum of the exponent of the k over k factorial. So what we'll do is we'll define matrix exponentiation to be plugging in the exponent into the Taylor series for e to the t. Let's see what happens. So recall that e to the x, that means 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on. And what that really is 1 is x to the 0 over 0 factorial, x is x to the 1 over 1 factorial, and so on. So that's the Taylor series for e to the x. And we'll define e to the at to mean plugging at in for x. So we're just plugging into the Taylor series. That's all this is saying. So e to the at, that means at to the 0 over 0 factorial plus at to the 1 over 1 factorial plus at squared over 2 factorial, and so on. And remember that here A is an entire matrix. It's a matrix of constants. So this is why we introduce matrix powers. This would be the matrix A times itself, and then times t squared. And what we're interested in is what is the derivative of e to the at. So take the derivative of both sides, and let's see what happens. Okay, what's any matrix to the power of 0? That is I. And here, this is a to the 1 times t to the 1 all over 1. This is a squared t squared over 2 factorial, and so on. And now we're taking the derivative. And remember that the derivative of a matrix is the matrix of the derivatives. We just take the derivative of each component. So when we take the derivative of the identity matrix, this guy is constants. And that means that its derivative is going to be the 0 matrix. What's the derivative of AT? Well, remember that the t goes to all components, and the derivative of a constant times t is just the constant. So this will become just a. Likewise, over here, t squared goes to all components. When we take the derivative, we just pull down the 2 in all components. We can pull out the 2, and the point is that all we do is derivative of t squared is 2t, and we have 2a squared t over 2 factorial. Here, derivative of t cubed, pull down the 3, we have 3a cubed t squared over 3 factorial, and so on. Okay, now, all of these guys have an a in them. So let's factor out the a. We'll put it there. When we factor out an a from a, then we're left with, it would be 1, but it's the identity in the case of matrices. A times I is that a. Over here, we factor out the a, and now we have just 1a left, and a times t, and 2 over 2 goes away. Over here, factor out the a, that's now in a squared. The t squared is still there, and 3 over 3 factorial is, remember that 3 factorial means 3 times 2 times 1. We got rid of 1 3, so now there's just the 2 times 1 is left. Over here, 4 over 4 factorial. 4 factorial is 4 times 3 times 2 times 1. Get rid of the 4, it's 3 times 2 times 1. So down there, there's a 3 factorial left. And we factor out an a, now that's an a cubed, and the t cubed is still there. Okay, and look what we have here. This whole guy is that whole guy, which is that. So we wind up with a times e to the at. So that proves that the derivative of e to the at is a times e to the at if we define matrix exponentiation to mean plugging into the Taylor series. So what we have shown is that the derivative of e to the at is a times e to the at. That is what we just showed, where we define e to the at to mean plugging at into the Taylor series for e to the x. And therefore, e to the at satisfies this differential equation. Why? Well, e to the at prime, we're asking, is that equal to a times e to the at? Well, the derivative of e to the at, we just pull down the a, that's a times e to the at, and that is indeed equal to a times e to the at. And furthermore, the columns of e to the at are a fundamental solution set where x prime equals ax. This is because since e to the at satisfies x prime equals ax, so does each column of it. So each column of e to the at will also satisfy x prime equals ax. You know, just look at the first column over here. The first column here must be equal to the first column here after the matrix multiplication, since matrix multiplication is defined column-wise. So this implies that each column is a solution. And furthermore, the columns are linearly independent, and that's because e to the a times 0, plugging in t equals 0, is the identity matrix. And the identity matrix has linearly independent columns. No column in the identity matrix is a scalar multiple or a sum of the others. And for columns to be linearly dependent, one must be a scalar multiple of the others everywhere, including at 0. So e to the at will be an n by n matrix. After all, each of these terms is still an n by n matrix if a is, and then so is the sum. So e to the at is an n by n matrix. It has n columns, where a is n by n, and those n columns are linearly independent and all satisfied, and therefore are a fundamental solution set. So full stop, the columns of e to the at are a fundamental solution set to x prime equals ax. Okay, let's do an example computing a matrix exponent. So x prime equals 1, 1, 0, 1x. This is the guy where we did that example and it has only one eigenvalue, and therefore the eigenvalue eigenvector method doesn't work, and we must use matrix exponentiation. Let's try doing this by plugging directly in to the Taylor series. So e to the at, that is the sum from k equals 0 to infinity of at to the k over k factorial. That's just plugging into the Taylor series for e to the x, which remember is sum of x to the k over k factorial. Okay, and at to the k, that's a to the k t to the k over k factorial. And now, if we can find what a to the k is, then our lives will be a lot nicer. Okay, so a is 1, 1, 0, 1. What's a squared? Maybe we can find a pattern. A squared is this matrix times itself, which is 1, 2, 0, 1. What's a cubed? If we take this matrix and multiply it by 1, 1, 0, 1 again, then the first column will be 1, 0 again. And the second column, taking the 1, 1 and sprinkling over and adding, we have 1 plus 2 is 3 there, and 0 plus 1 is 1. So do you see a pattern going from here to here to here? It looks like the only thing changing is this upper right, which goes 1, 2, 3. And in general, a to the k will be 1, k, 0, 1. So this is a nice matrix where we can actually find the kth power pretty nicely, and we get that. Okay, so a to the k is that, and we want to find this sum. Okay, so we have that e to the at is this so far, and t to the k and dividing by k factorial, those are just scalars. And we distribute those to all entries of the matrix here, and we have that. That's just multiplying each entry by t to the k over k factorial. And we're adding together all of these matrices, and adding together matrices, that just means adding together each component. So this is the same as distributing the sum inside all of the components like this, and adding together 0 a bunch of times is still 0, and we have that. And now what we do is hopefully we can identify each of these as a Taylor series of something that we know. So we know, for example, that e to the x is the sum from k equals 0 to infinity of x to the k over k factorial. Does this look familiar? Yes, it's just that, except with a t instead of an x. So this guy is just e to the t. It's the Taylor series for e to the t, and this guy is the same. And now we need to find what function this Taylor series is of. It might be helpful to write this out. So plugging in 0, k equals 0, we have a times 0. Plugging in k equals 1, we have a 1 times t to the 1 over 1. At k equals 2, it's this, and so on. And this is looking pretty similar to an e to the t of some kind. Okay, so 2 over 2 factorial is 1. 3 over 3 factorial, we have a 2 factorial left. The next term will be 4 over 4 factorial. There's a 3 factorial left, and so on. And it looks like if we factor out a t, then it will look like this, because we want the leading term to be a 1. So this is the same as t times factoring out. We have a 1 plus t squared over 2 factorial plus t cubed over 3 factorial plus and so on. Okay, but that guy is this, just with a t. So this is t times e to the t. So we had that e to the at was this matrix, and we found that this is the same as e to the t up there. That's the Taylor series for e to the t. So is that. And we just found that this is the Taylor series for t e to the t. So this is the matrix exponential. This is what e to the at is, where a is 1101. And we saw that the columns of the matrix exponential form a fundamental solution set. So the general solution to the system of differential equations x prime is 1101x, this guy, will therefore be that x is c1x1 plus c2x2, where those are the columns. And this is therefore our general solution to this system of differential equations. This first guy here, note that this first guy is c times 10 times e to the t. This was the one solution that we got via eigenvalues, eigenvectors. And then this other solution is the one that no eigenvalue, eigenvector method can find, because it's not of the form k times e to the lambda t. It has a t there instead. So matrix exponentials were necessary to find this. Okay, so in this case, we were able to solve this by plugging directly in, because a to the k had a nice pattern, and we were able to find that 1101 to the power of k was 1k01, and therefore when we plugged in, it became pretty nice, and then we could identify Taylor series and compute the matrix exponential. Another case where it can be nice to plug in directly is no-potent matrices. A matrix A is called no-potent if a to the k is 0 for some k. And note that once we get to 0, then everything past it will also be 0. Because at that point, then we're just multiplying by 0 again and again and again. And in the case that a to the k is 0 for some k, then this sum becomes a finite sum, because once we hit the point where a to the k is 0, then everything past it just disappears. So for example, let's compute e to the at, where a is this matrix. And that would be the same as solving the system of equations. This, just reading off what the rows are. If we were to convert this into standard matrix form, then it would look like this. So e to the at is a fundamental solution set to this system of differential equations. Okay, so if we really wanted to solve the system of differential equations, let's take e to the at, and we can plug directly in. So e to the x is 1 plus x squared over 2 factorial plus and so on. And if we were to write this out, then because a to the 0 is I, that 1 becomes an I, and we have I plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial plus and so on. Okay, so there's I, and at is that times t, and a squared, so we need to take this a and multiply it by itself. And we certainly can do that by hand, but you can see that this matrix multiplied by itself is that. So we got that a squared is this, and then that was times t squared over 2 factorial. And then the next term will be a cubed times t cubed over 3 factorial. What is a cubed? So if we take this matrix and multiply it by a again, we could do this by hand, but just to save time, you can see it's a bunch of zeros. So this is what we mean by nilpotent. And at this point it's 0, so if we multiply it by the matrix again, we're just multiplying it by a bunch of zeros. It'll stay a bunch of zeros, and likewise for every term after. So a cubed is 0. That means it's a giant 0 matrix times t cubed over 3 factorial, and then everything past this is 0 as well. So all of those just don't exist. And this infinite sum becomes a finite sum. It just is adding those 3 matrices together. And remember that what this was plugging into here. That's I plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial. And we have found that everything past here is 0. So e to the at is just the sum of these 3 matrices. Remember that we need to distribute that t inside and distribute that t squared over 2 inside. And then we add together the corresponding entries. So up here, we have a 1 plus 1 times t plus 0 times t squared over 2. So that's a 1 plus t up there. Next, we have a 0 plus 1 times t plus 0. Over here, we have a 0 plus 3t plus 0. Here we have a 0 plus 5t plus 3 times t squared over 2. So we have a 5t plus 3 halves t squared. In the middle, 1 plus 2t plus 3 times t squared over 2. 1 plus 2t plus 3 times t squared over 2. And so on. So we have our matrix exponential. There it is. And that means that these three columns form a fundamental solution set to the system of differential equations with that matrix x prime equals ax. Okay, but unfortunately, most matrices are not nilpotent. So this is great when it works, but it often won't. And most matrices don't have nice patterns when you take the matrix squared, cubed, and so on. So we need something more general to deal with the rest of the cases. Fortunately, however, and amazingly, we can use our knowledge of Laplace transforms to compute e to the at. So we know that e to the at is a solution of x prime equals ax, and e to the a times 0 is I, because when we plug in t equals 0, everything past the first term in the Taylor series, and the first term, remember, is I, goes away, so e to the a times 0 is I. And that means that e to the at is a solution of the initial value problem, x prime equals ax, since it satisfies that, and x of 0 equals I, since when we plug in 0, we have I. Now, what we'll do is we'll take the Laplace transform of both sides of this, and remember that the Laplace transform of y prime is s f of s minus y of 0, and in the same way, the Laplace transform of x of t is where we call the Laplace transform of big X, little x, s x of x minus big X of 0. So it's saying that same thing. And Laplace transform of a times x is a times the Laplace transform of x. So why is this legitimate for matrices? Well, when we take the Laplace transform of a matrix, that means we take the Laplace transform of each component. Same as when we take the derivative of a matrix, we're taking the derivative of each component. So this thing applies to each individual entry of the matrix, and then we can pull out the S from the matrix since it's everywhere, and write it as a difference of two matrices, one of which is scaled by S. Okay, but x of 0 is I, so then we can rearrange it to look like this by moving this I to the other side, now it's on the right, and moving the ax to the left-hand side, now ax is on the left, and factoring out the x of s. So the intermediate step here is we would have s times x of s minus ax of s equals I, after we move that I to the other side and subtract that from both sides. But s times x of s is the same as s times I times x of s, since multiplying by I makes no difference. And now we can factor out the x of s, and we get that. And what we want to do is solve for the Laplace transform. Remember, this guy is the Laplace transform of big X of t. And how can we solve for the Laplace transform? Well, we learned that if you have a matrix equation, say ax equals b, what we can do is multiply both sides on the left by the inverse of a. We saw this in the chapter 8 preliminaries. And then a inverse times a is I, and I times x goes away. And in this way, we can solve for x. So what we'll do is multiply both sides of this by the inverse of this whole matrix. So that means that little x of s is I times the inverse of that matrix, in the same way as this happens. But multiplying by I doesn't change it, so little x of s is the inverse of si minus a. But little x of s was the Laplace transform of big X of t. And big X of t was e to the at. So we have that the Laplace transform of e to the at is the inverse matrix of si minus a. And therefore, taking the inverse transform of both sides, e to the at is the inverse transform of the inverse matrix of si minus a. So there we have it. That is a formula for the matrix exponential. What a beautiful result. So let's illustrate using this same system that we dealt with before, where we were able to find e to the at by manually plugging into the Taylor series, but now we'll find it using our newfound formula. So we know that e to the at will be equal to the inverse Laplace of si minus a inverse, and s distributes, so that is s0, 0s. So we want to find the inverse Laplace of the inverse matrix of this. And the inverse matrix, we learned in the chapter 8 preliminaries that the inverse of a 2 by 2 is this formula. So we have 1 over AD minus BC. There is AD minus BC. And then in the main matrix, we swap A and D. Okay, they are swapped, and put minus signs by the B and C. And here we're subtracting 0, and this is s minus 1 squared. And this guy out here is just a scalar. It applies to all elements. So s minus 1 over s minus 1 squared is 1 over s minus 1. 0 over anything is 0. We have a 1 over s minus 1 squared, and an s minus 1 over s minus 1 squared. So the matrix exponential will be the inverse Laplace of this. And the inverse Laplace of the matrix means the matrix of the inverse Laplaces. So we want to find the inverse Laplace of each of these. So in other words, we can distribute the inverse Laplace inside each component. And now we need to brush up on our inverse Laplaces. So inverse Laplace of 1 over s minus 1, that was one of our basic ones, and that's going to be e to the 1t. Inverse Laplace of 0 is 0. And for inverse Laplace of 1 over s minus 1 all squared, that looks like a translation. Specifically, 1 over s minus 1 all squared, that looks like an f of s minus a. So our thought bubble is, what was the inverse Laplace of 1 over s squared? Well, that was t. So therefore, inverse Laplace of 1 over s minus 1 squared will be t times e to the 1 times t. So we therefore have our matrix exponential. It's the same matrix that we got before, of course, by manually plugging into the Taylor series. And this is certainly nicer than plugging into the Taylor series. And for most matrices, when we take a to the power of k, it doesn't have a nice pattern to begin with. And this is what we would have to do. So let's solve this system. X prime is this matrix times x by finding x equals e to the at. So when you're given a system from scratch, your first impulse should be to find the eigenvalues and eigenvectors. And if we were to find the eigenvalues and eigenvectors of this, first we would find determinant of a minus lambda I and set that equal to 0 to try to find the eigenvalues. And once we got to this point, then we would see that there is only one eigenvalue. And that means that we will not have enough eigenvectors. So that means that we must use the matrix exponential. So that is how you tell, similar to what we did in the beginning of this section. So we have to use matrix exponentials to solve this system. And doing so, e to the at, we plug into our formula. And the s distributes there, and when we subtract, we'll have, as in the previous example, this matrix. Mind your double negatives. We have a negative negative 4 is positive 4, and so on. And we are taking the inverse of this matrix. So inverse matrix formula, 1 over AD minus BC. And we swap the main diagonal. Okay, those two are swapped, and we stick minus signs by the others. And since we'll want to take the inverse Laplace of each component anyway, and we're dividing by something, our first inclination should be to factor the thing that we're dividing by. That will help with finding the inverse Laplace. So let's FOIL this out, and then hopefully we can factor it. FOILing out, we have s squared minus 2s plus 1. And this guy factors as s minus 1 squared. So we distribute that dividing by s minus 1 squared to all components, and we want to find the inverse Laplace of this matrix. All right, so now we find the inverse Laplace of each of these, and we'll have our answer. We have that. I color-coded these two because those are a direct application of this first translation property. Just like in the previous example, 1 over s squared becomes just t, and this will be t e to the t. This guy, that minus 4 is just a scalar, we can pull it out, and it's negative 4 t e to the t. And then for the upper left and lower right, we need to do some work. Let's work on those over here. So that upper left guy, that was inverse Laplace of s plus 1 over s minus 1 squared. Here's a trick. We can think, wouldn't it be nice if that were an s minus 1? Then it would cancel out. Well, let's make it s minus 1, and then add 2 to compensate. S minus 1 plus 2 is s plus 1. But the thing is that now we can write it in the following way. S minus 1 over s minus 1 squared is 1 over s minus 1. And then we have a plus 2 over s minus 1 squared. And then we can distribute out the inverse Laplace. And we have that this is e to the t plus 2t e to the 1 times t. This guy being our same first translation. So we found the inverse Laplace of the upper left. And now we can do a similar analysis with this guy on the lower right. Okay, and our other guy on the lower right was inverse Laplace of s minus 3 over s minus 1 squared, and we do the same thing. Wouldn't it be nice if that numerator were s minus 1? Well, let's make it s minus 1, except that was a minus 3, so then we subtract 2 so that it stays equal. And we'll put parentheses around that. And that's s minus 1 over s minus 1 squared is 1 over s minus 1 minus 2 over s minus 1 squared. And this is the same guy that we had here. This is a translation of the inverse Laplace of 1 over s squared, which we know is t. So this will be t times e to the 1 times t. So we found the inverse Laplace of the lower right. So we have found that this guy is e to the t minus 2t e to the t. So we're done. We found the matrix exponential. And remember that the general solution is an arbitrary linear combination of these two columns, x1 and x2. So the solution to this system of differential equations is x is c1 x1 plus c2 x2. So our actual solution to this system is that x is this arbitrary linear combination. All right, that does conclude the entire course. Congratulations, and have a great one.